Welcome back to the live stream of the lsm-tree key value store that I'm implementing. So I've made some progress ever since the last video, or I've changed a bunch of stuff. I can't remember exactly where I was, but I've changed a lot of stuff in the way I structure the data. So if you look at, so I have like these, actually let's go to the header file. So I've kind of structured things. So for the data I have like special structs now, and then for any conversions I, for serialization and deserialization, I have specific methods. So it's all more structured. There's an interface and it's easier to test and things like that. So right now I'm at the point where, well, if you look at the tests, so there are some interesting cases that are failing, but I can show you. Yeah, I have like basically I've gotten to the point where compression and writing works, if I'm not mistaken. Let's go to persistence. Where is it? Yes. So I have the compress and write. Yeah, this works, I think, from what I've tested out. So if I go to test persistence, yeah, I mean, if I go make test persistence, should work, hopefully. Okay, well, I have some, what is this? Make files. Test persistence. Lib, that's fine. Where's this? Test persistence source. No, I just basically need. What's the problem? Persistence. I think it doesn't have all the links I need. This is what I'm guessing. Persistent OBJs. Okay, I think the L string. Right, abs. Lib lstro. I think it's this, right? Yeah. Will that work? SSD pair get size. Okay, let me check what the problem is. KL string size referenced from. Maybe we can redo this as well. Will that help? Okay, it's failing during linking because of what exactly? Okay, and the skip list is not there in the list. I mean, this should be there, right? Wait. Right, I mean, look. Persistence has block, which has core. So I thought it would be there. If you look at the command, wait, let's do a clean and sorry, let's go this. Oh, okay, now we get something different. Okay, hmap-c. Now let's go to hmap-c. Yeah, I think this, not here. Where is it? I don't think that's needed. So this works, but this doesn't. What the hell is it with these make files? I really don't get it. So if you clean and make, it's a different output versus LOVJ utils. There's no utils at all. Okay. Test utils, OBJ. Whatever. I don't understand this. Ah, okay, so yeah, okay. So this is still an error. KL string length size is defined where? I guess I think we need this. So you can have a static const, but this is what? Oh, there's this. Okay. So this is exported. I think this needs to be defined here, maybe. Oh, okay, that improved. Cell as get data. And this is in the skip list, and I guess the skip list is not in the core. Do we have the skip? We don't have the skip list, really. That is a core object. str. Skip list strh. Okay. Yeah, okay, that works. Wow. I mean, it all makes sense, but I I had AI generating this, and I don't know how to do this in a better way. This is all a bit weird. I would like to just build everything and not care, like every time. Anyway, who cares? Okay, so we're good, and I think if we go to test block, we get something. Okay, test block. We gotta fix these. So we've got this is failing, surprisingly. Oh, okay, yeah, I know what the problem is. So we're doing a search. Did I forget to commit the? Yeah, okay. What is the problem here? I think I fixed this issue because I work on a different machine as well. Okay, but what's my data? My data. Again, why? Oh, this isn't working. I need to go to the definition and not the header. This is very annoying. So I have to test, compress, and write. Do I need this test still? I don't think I do. No, I don't. Okay, I can just remove this. This doesn't need to exist. And test hmapc. I think this can be just yeah. Okay, great. And now can I try this? I hate this because I don't get this comptb stuff. What are the objects here? It should be everything, really. And the reason it doesn't work is because I'm going to the test utils, and I guess the test utils aren't included. Yeah, I would. Object, I would say test utils object, but that's defined later. Is that fine? Okay. No, let's. Thank you. No. Why doesn't this work? This is very frustrating. So comptb should include. I guess. Do we have the test? Okay, test use. Well, tester is tests, so it should include it, really, technically, right? Test utils src, test utils. These are filtered out. Okay, test utils src. Test utils obj. Come on. Where was I? No, I was here, and then, no, I was here. Compile commands. Really? Do we not have test utils anywhere? What? Dude, I did all that to... So what a waste of time for everyone watching. I mean, well, nobody's watching, but what a waste of time anyway. Technically not needed. I have no idea what to say. Okay, well, we're gonna have to ask. Claude. Come on, Claude, help me out. Okay. That didn't really work. Oh my god. It should be. If you have to do this kind of stuff, it feels like something's going terribly wrong. But okay. Nonetheless, I mean, do we have the test? Well, we certainly don't have the test utils objects. That's twice it says. I am using bear make comptb. Alright. Can I go to my compile commands? Utils. Well, now I see them. Great, so hopefully it works. Doesn't. Oh wait, my utils were always here. Right, that's right. My utils were always here. Okay, so my problem is when I do go to definition for a file in util, I get sent to utils.h and not the implementation. Ah, can we just fix this? I'm having a big deja vu. I feel like I literally have had this conversation with... I've had this exact problem. Cache, clang D. Alright. Nope. Okay. Oh, what a waste of time. You'll see. Alright, let's try this. Build, compile, commands, JSON, make comptb. bruv. This thing sucks. All right, let's start from scratch. Please work. Yes. Yes. Okay, awesome. And I'm gonna change my CompDB goal because I don't want to do all this. Make file CompDB. By the way, you can go CompDB. Do I have my? Okay, I need to download a clipboard manager. Or actually, whatever, leave it. But I do need my clipboard manager. I don't have it. Okay, great. Applications. Okay. Okay, we're good. What? Okay. So let's check the test that fails, which was okay. Double get. Yes, I wanted to see. Okay, so this is looking for. So this only has multiples of 2 as keys. And if I go to block, I am looking for 31. So indeed, I can't find it. But wait. Yeah, so it can't be 1, of course. It has to be 0 in this case. Or I will just change. Yeah, I'll just keep the standard. That was just a test. But I need a better test set anyway. I think whatever I have here is just, it's okay-ish. But I'll leave it. So we have this. Okay, great. Oh, and every test passes now. Great. So I will go delete all these printfs in the implementation. Yeah, you have to do this, by the way. And using start plus n minus start or 2 doesn't work. The reason it doesn't work, FYI, is because at the last iteration, this becomes negative, and yeah, that doesn't work. When this becomes negative, you're off by 1. Let's put it like that. So just a side comment there. But I guess, yeah, there are other ways. I think technically what you could do is this and this as well. Start plus n minus, wait, n minus start over 2. You can do this, and then I would say here, for the last iteration, I have a feeling you could just do end, but I'm not sure. Because when you don't have a match, it means okay, you will usually be at something like n and n plus 1. Wait, let's go to comment mode. Okay, so you usually would be at index n and n plus 1. So let's say 4 and 5. Okay. That's your last check. Okay, and you will have 2 cases. You will have, right, you will have either this or this, whatever you check. So okay, so the mid, right? So that's start, end, and then mid is, of course, 9/2, 4.5. So mid is 4. It's always the lower one. Mid is 4, and then you check 4. If it's less, so okay, we're gonna have the case where then you get 6 and 5 is one case. So let's write 1 is 6 and 5, or 2 is or A and B, and the other is where that stays at 4 and this becomes 3. Okay. And I think at the end what you want is there a consistency. Like, I think you just want to return 4 anyway. When you're in this case and it doesn't match, you want to return 4. I'm guessing, right? Okay, because, right? And here the mid will be 11/2 is again 5, and this is 7/2 is 3. So they're quite off, right? Am I right? Yeah, because end becomes mid minus 1. I think you always want 4. Like if you're searching, right? So you've isolated, you're searching an array of 2 elements. You're searching an array of 2 elements, and you want to know. Oh, it doesn't matter. You want to know if your key is. Okay, let's explain the problem. Okay. So I have. Let's say you have the key 10 and the key. Okay, let's do this. At index 4, you've got 10 and 15, right? Or let's use strings to not get confused. Okay, you have this, or A and C. Okay, and you are searching for B. I think you cannot be searching for anything before that. Or let's use C and E. So maybe, so F. I don't think you can be searching for B or for anything else because you wouldn't be in this position ever. Okay, and so it either, I guess the result is it's either equal to this or equal to this, but if not, it's going to be in the middle. So you always want to start, because then, right, this is just an index, it's a sparse index. So then you will continue to do a linear search here. So the index has only these keys. So you always want to be 4, basically. When you have 2 numbers left, you want to be this. But somehow you can't guarantee that. You basically want to be the average of these two, right? You want to be the last time mid was that. The problem is that you update at the end. Will this work? Okay, stupid question. What if we just do this? Like you just update in the beginning, which means at the end you don't update at all, and mid should still work, I think. No. Why doesn't this work? Let's see, after, and we go S and end, and we go start, mid, end. Okay. Right, that's after. And let's go to, so loop, we'll call this. And let's try these two. Okay. I didn't say that. Okay, so in the loop, I need a new line here. Okay, so right, when it's just 0 and 1, and so would this work? That's what I'm trying to say. Oh no, what the hell? See, that's very interesting. So that works, which is you give up. Why? Because when you're at 0, that should be your last iteration, right? It shouldn't actually. You're missing out on one more check. Because so you would check, like you would check 4, then that wouldn't be equal, that would be bigger. So you would go start is mid plus 1. So by the way, I was completely wrong. Start is mid plus 1. And then you would break the loop, but now you still have to run this check. Okay, you have to run this check. And the other way around is end is mid minus 1. So that's correct. So you've got either 5, 5 or 4, 3, right? Is that right? Right, because yes, mid is 4. And then this goes up by 1. And here, no, this should be 4. No, 3. End is mid minus 1. Okay, and here mid is 5 again. And there it's 3. So that's fine, that's far. Yeah, no, you need to check. You can't do this because you need to check. You need to check this as well. Because if it's an exact match, you want to stop. You don't want to. So you check if this is a match, and then you go here and you check that if that's a match, and if not, then it's always this. So if neither is a match, and I don't know what the nicest way to do this is. Because if you keep this loop, then you have to wait until they go right. And then what happens in the next iteration is going to be less. Right, so this is going to be, so yeah, then you have this case, and then you check if the key, right, what are we comparing? We're comparing the actual key with so the key that we have is going to be greater than 0. So end has to become mid minus 1. So then you go this. So it's at the end. Here mid is 5, 9, 4. And I think this is the problem. Yeah, that's the problem. So I can't find a clever way to solve this. Whatever. There's probably something, and I'm just being very, very dense. But yeah, I just... The negative part is what ruins it. No, wait. According to this theory, mine should fail each time. And this is not great. Okay. Okay. We have to restart. So, we are at index 4 and 5. So this is 4 and this is 5, right? So this is 4, this is 5. Okay. So that's start is 4, and is 5, and then mid. Okay, so we started the loop, then we compute mid. That's 9 divided by 2, 4.5, 4. Okay, so we search 4. So we look at compare C and F. Of course, C is less than F, which means we have to go look into the second half, right? We have to go start is mid. So this will be 0. Therefore, we go start becomes mid plus 1, 5, and becomes 5. Then we compute the new mid is 5, obviously. Then you do compute E. Sorry, I'm searching for D. Something in the middle. And sorry, E and F. Right, thus far we're still good, and this is greater than 0. So then start remains the same, and this becomes 4. Right, this becomes 4. So this is the only. Well, this is the one case. I think this is the only possible case. Like you can't have both. It's always going to be. We're talking about the in-between case, because if it's exactly this, then you get that, and if it's exactly that, okay. So when you're in between, and it can't be greater than this. It's impossible. You wouldn't get to this point where the thing you're searching for is greater than that or less than that. I don't. Well, there's one edge case, which is. Oh, we'll get to that. We'll get to the edge cases as well, because you can have the case where your entire array is, let's say, B, C, D, and you are searching for A. Oops, you're searching for A. So we'll tackle that. And so this is mid is 4 again. If you use the proper mid. So if you use this, it'll fail. Why? Because you will have 5 plus the difference is minus 1 over 2, and minus 1 over 2 gets rounded to minus 1. No, wait, minus 1 over 2 gets rounded to 0 if I'm not mistaken. Right, so if I go main void, so if I go D is equal, sorry, int D is equal to minus 1 over 2, yeah, so that's the problem. It always gets rounded like towards the positive side. Even if you had 3.5. Oh, I didn't even know that. Wait a second. Oh, I didn't recompile. What am I talking about? Of course. Yeah. So you can see it doesn't get smaller, but it gets rounded to the positive side, and that causes a bit of a problem there, because this is 0, so your mid is 5 instead of being 4. Okay, so here it should be, of course, 4, and that's good. That's what you want at the end. So isn't that always equal to the end? Because, well, because you will always have, at the end you will have n plus 1, you'll have this, right? Plus e over 2, and that's 2e plus 1 over 2, and that's e, always. So why, what if we do this? It should work. Of course. Now the edge case is, right, you start with 0, and is 2, mid is 1. So you compare C with A, that's less, so then you set, just keep the 0, you set this to, end becomes, you search in the first half, because the thing you're searching for, right? So n becomes 0, m minus 1, so m is 0, so you compare B with, actually let's make a more interesting case. Okay, so that's 3, so mid is again 1, again the same result actually. Yeah, it doesn't matter. Let's keep this. So then I need to add more stuff. Then you compare B and A is again less than 0, and so that's the problem. So then start becomes 1, end is 0, and the mid is 0. So I guess yeah. So you're always one off. You're always one off, and therefore you can just take end. That's my guess. You can always just take end. You don't care. You just take end. And then no matter what happens, and I think it will work the same for the. Well, this is going to be an interesting case. So let's go to right. You compare that with z. That's evidently this. So start becomes 2, end is 2. Right. And therefore this is 2. So you compare d with z. It's also greater. Again, if it's greater, then this is tricky. This is why it doesn't work. So then end becomes mid minus 1, and this remains this. So actually you don't want end to be 1. Sorry, so then mid is, but mid is 1 again here. Oh, this is not great. Yeah, this wouldn't work either way. Wait. In the positive case, we take end is mid minus 1, and then you would break the loop. Well, no matter what you took, this wouldn't work. Because technically you should be returning. Well, yeah, you should be returning 2. So that's a bug anyway. Oh, why is this so... This should be so easy, and I'm missing something. The idea is that here I want to return 2. Wait, D? Oh, what am I saying? I think I made a massive error. C is greater than A. Look at this. C is greater than A. Yeah, and B is also greater than A. Look at this. So stupid. So then this is 0. And this is minus 1. So this wouldn't work here either. But and the mid would be 0, and that would work. The normal mid. And here it's the opposite problem. Right? So you go start, and then again in this case you go start is mid plus 1, so start is 3, and is 2, and mid is 2. So the mid is correct in this case because mid is correct in both cases, and the end is correct in this case, but it's not correct here. Yeah. I'm thinking. So what I would do is end less than 0, then 0, else end times k reciprocal. This is what I would do. Because this is, or you take the, or rather instead of doing a branch, just do the calculation. The only thing I'm afraid of, I don't mind doing the calculation, it's just overflow. That this is why I'm using this formula. It's for the overflow, and I'm like, how do you handle overflow here? Otherwise. And that's why I'm doing the check. Basically, what is an efficient way to calculate this? It's not E. That's the problem. It's not E because of this case, the negative case. So think about this. This is 0 in C. So what is the most efficient way to calculate this? I'm gonna, I don't want to ask Claude. What's the most efficient way to calculate E plus E plus 1? How do you do this? That also handles the negative case and handles overflows. Or do you do E over 2 plus E plus 1 over 2? I guess this would work, right? Yeah, this would work in the negative case too. I would say this is so ugly, but I think this is right. It feels very ugly, and I feel like there's a much nicer solution. And I'm not all. I mean, I'm not even testing the edge case, so the test passing doesn't mean a thing. So that's why it would be worth testing in the test. Where is the test? It's the test. Yeah. What if you were searching for something smaller? So A and then Z. Right, of course, I'm not expecting to find it here. Oh yeah, I'm getting -1. Sorry. Yeah, of course I'm expecting, because at the end I return. What I return? I return the position as a negative value from which where I got left. Oh, I don't even know if this is right. I think I want to return this. I think I want to. So technically for z, I would like to see -1, which was correct the last time. Yeah, I would like to see -1. Oh, okay. Okay, I think this is also wrong. I'm expecting to see -1. So this is wrong, like, it should be -1. It's not working in the edge cases at all. Honestly, I think if end is 0, I should. If end is -1, I shouldn't search. Should break. So I still have to do that check. Like, you can't search if it's smaller than where your index is. You're never gonna find it. So I think if I would say right, because you can't do anything. So we would stop. And otherwise, I think we can just continue with end here. No, I think this is fair. And here as well, I think it's just end. Yep, that's correct. We need a better. We need a bigger index. Because, well, this is 32, and I only have 64 in the test. I look at the test. Look at this. To have more restart points, let's use 16. Okay, let's go to this block. A should give 0. Yeah, no, this isn't even correct. I need something like, the problem is I have an asymmetry, like it's like this. So if I have keys, let's say 1, 2, 3, 4, 5, 6, 7, 8, I would have an index like this. Oops. I would have an index like this, like 1, 4 or something like that, right? Which means if it's smaller than the index, I know for chance it doesn't exist, but if it's bigger than the last one, it could still be here. Like, unless I had an index here as well, then I would be able to partition, like it'd be like, yeah, okay, if it's bigger than this, it's not there. If it's smaller, it is. So you would have like these bounds, and that would kind of simplify the situation also with what you return. So you could say you would return then where you were searching for as a minus value, which could be also 0 technically. Let's call it 0. Yeah, you could say you would return, and then you would return negative. Okay, well, you need to return a value for when you found it. You need to return a value for the last index you were searching for, and you need to return values for when it's smaller and when it's big. When it's basically, so you have the case where it's found, so you return a value for that special value, and you have the case where it could not be found, and then you have to specify in which range it would be. So you specify 0 when it's in this range, you would specify 3 when it's in this range, you would specify 7, I guess, when it's in this range, but what you would you specify for here? Kind of like hard to say. I don't know. It doesn't matter. Kind of works now, and I need more test cases, but I will add them later. So this I expect to find, therefore we do this, and it works. Yeah. Yeah, so by the way, the search is a prefix encode. Well, the keys are stored as a prefix encoding. So, for example, I have keys 001, 002. So, when you start, there's no shared prefix. You store the whole key, and then you only store these. So these are the actual things that are stored. This is calculator, but this is what you store. So you store 1, 2, because this is shared, right? 1, 2, 3, blah blah. Until you reach, I think, what is it now? 32. Yeah. So every 32 things you have a full restore. And yeah, you can tell. So that's going to be, so this is you're searching for, and this is what you're comparing against. So you do a comparison like 0, 3 plus 1. So you concatenate these, and then you compare, and you find it. This should also be found, but this would be searched elsewhere. Obviously, you start at 32. So again, you can see another restart point. So at the 33rd key, you store the full key no matter what. So you have this index with restart points. Yeah. Okay, it doesn't matter. That's good though. Okay, so then what do we have? So we tested this. So we've got search working. We've got search working. Persistent C. What is it? Search in SST, right? That's the function. So this is not good. I'm not using that. Search in SST. So I'm using, what am I doing here? I'm doing manual work. This is what the code used to look like, by the way. Like, it's so bad. Because I used to not even read it into a structure. Well, I didn't even have prefix encoding when I wrote this code. So yep, so now it looks like this. I've got these weird data structures, whatever. Right, so this is what I do. I go to the file, I go to the end of the file. I read the footer, and the footer contains some information. So it contains where the index is to be found, how large it is, and where the index... Actually, what is that? The index restart. Yeah, the index itself has restart points, which I didn't understand why, or I've forgotten why it has restart points. Well, of course, like it's very simple. The whole idea of restart points is, like, how do you do binary search if your data is not fixed size, or like of uniform size? And you can't. The answer is you can't. The whole idea of binary search is that you know where to jump to be in the middle, and so the only way that works classically with arrays is that each element in an array has the same size, so it knows where to jump. And usually when you do string search, with binary search with strings, the reason that it works normally is because the strings are stored as pointers. So you just jump to the pointer, and the pointers are fixed size, so you can just like jump in the area of the pointer, look at the value there, like chase that pointer, find the string, blah blah. Of course, in this case, we don't have that. So what you have to do is what I do is effectively the same thing. So instead of having like I'm comparing strings, which are variables length. So instead of having pointers in my array that I'm searching, I have offsets, which is the same thing. It's an offset from a pointer, from a start pointer. So basically, the restart points are my array that I'm searching in, and the indirection is through these offsets. So that's how you kind of search. That's why you have both. So you have an index, which is a bunch of keys, and then you have your restart array of the index, which is what you use as your index into the area of the data. So it's this level of indirection with offsets. It's basically how you would store. Like this is the only way, let's say, when you deserialize from disk, to do this without having to allocate again. Right? If you were storing something on disk, obviously you would need to know, and to do binary search directly, you would need to know, you would need to have the restart array. If you don't have the restart array, it means that you have to do a linear pass to find out all the offsets first, and thus defeating the purpose of the search. And so this is the only way you can store it for it to work. So you store the data first, and then you store the offsets into the data, and then you use this offset array to search. So you do start, and this has a fixed size, so you can go like, okay, 0, and end is whatever, 3. Then you go to mid, so you go to the mid object. It's an offset, so it's a pointer. You have to chase it into the actual data. You do the comparison there, come back, change. So you do your manipulations in the restart array, and then you use the data to compare like in the actual block. So it's basically a pointer. So that's what I do. So I deserialize. So I get the footer first. I read so I read the footer directly, and I think this works fine because this is padded in a way. Well, this is no padding done. So it's like when I memcopy from disk, it's literally just packed perfectly. Like there's no padding in the struct, which means I can just do that because there's no, when I write stuff to disk, I don't do any padding. Therefore, I want to, when I deserialize, if there's padding in my struct, it means that there's no match of the sizes. So that works. So I read the whole footer. then I know, okay, I go to the index offset. I know that I have an index size, so I take, okay, my index is basically from that point, right, first I allocate, and then I know that my index, after I've moved to that offset in the file, I know that that's my index. So I read into the index its exact size. I get my restart points as well, so because I've read them. So I have also the pointer. So now once I have the index contains the restart array itself, and then I know where that is. So basically the index offset is the offset within the file, and the restart array offset is also, I think, yeah, it's also the offset within the file. So you take the difference of the two, and then you get the offset for the restart array relative to the index. So that's why you can do like this array access here. And then we first search in the index section, and you do a binary search here. Again, I wonder if this can also be improved, if I have to be careful here. If you think about it, kind of do, I guess. Yeah, I think I need to fix this as well. And then I get some item, which is I know where to search from. So this is that. So this offset is the block that I have. So I go to the block start. There's a block header. I read the block header, which contains the original size and the compressed size, because the blocks are also compressed. I read the block. Then I deserialize the block, and then I search in the block. Like, makes a lot of sense. But I think the index search has to be fixed as well. I think, yeah. But since I always return item, I guess I'm good. Maybe. I mean, yeah, this is not... I think this is bad, because if your key is smaller than everything, then actually you should stop searching. It's the same problem, I would say. So, I would say to do should return null if the search key is smaller than the smallest key in the index, obviously. I think if I remember correctly, the way RocksDB does it is it stores in the index the differentiating key between... Oh my god! The differentiating key between the blocks. Something like that. Like it has a way to... So what it does is it has the last key in the previous block, and then the first key in the next block, and they're all always sorted. And then it finds the shortest string, exactly the shortest string that can sort of differentiate between the two. I don't know exactly what it does, but yeah. And I wonder if that... So if I have, I guess, my question is, if I have like block 1, block 2, block... I'm not gonna write that. Okay, so I go 1, 2, 3, 4, 5, 6. I wonder if the index is here, right? So let's be more specific. So here an element, 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 and here an element. Actually, this is just annoying. Right, so let's use these. Like if it's like this, so that you know that if you have like, especially these two, that you know you're out. I guess that would make more sense. Right? I mean, very valid question. That would simplify the search. But the way I build the index, I don't think that's true. But I maybe should make it. Yeah, so there's a bug here, but it's okay. It's incomplete. So we've got search. Yeah, I'm gonna take a break because I can't think straight. I need to eat something. Break time. somehow I'm really unmotivated to fix this. Am I testing index search anywhere? Index search, what's it called? Yeah, am I testing? Well, I am. Interestingly, I am testing this. That's very good. Correct. So what do I have? I have, oh, but I think I need to also, so I didn't test one edge case. Right, I did test this. And so I go A. And if I go make test passes, but you shouldn't get that offset. Technically you should be getting null, right? Think about it. Should be getting null. So this is bad. Works otherwise, but this is bad. Again, it's, I think if end is less than 0, you just return null. And so you just say test assert null. Do they have it? This autocomplete kills me because, like, when you delete it, it still gets stuck to. Look, it doesn't suggest everything else. I have to do this. I hate it. Oh, yeah, I think this is right. Ooh, segfault. Segfault. Why do we have a segfault? It's returning null. I'm asserting that something's null. It's not working. Okay. Where is it segfaulting? Ah, come on! Don't do this to me. Why is it segfaulting on the? Wasn't segfaulting before? It's a normal check. Alrighty, I gotta get my trusty. Can I start this? Thank you. Yes, I want to open it. Print fs equals. No, none of that. I don't have it. Okay. Print f as and well, mid and end. Let's try this. Alright, well. LLDB, baby. Run. Why? What the hell? Oh yeah, well the test should. Oh, okay. Didn't I? Oh, are you serious? Didn't I save this? I didn't save it. Really? Okay. What are we talking about? Oh, sorry, there is an H. Oh, there is one. Didn't check. Crazy. Okay, I didn't see that. I will just go. This is bad. Like, it's really not. How did I miss this case? Like, why would you search if it's smaller? that. Null item 6. Let's so a is smaller than smallest key full plus null. Okay, that's correct. G. So we've got that right, but I think we need to account for this in right. If not index item, then you've gotta return null. I hate nulls, but that's what it's supposed to be, because whoever uses this, well, this uses it. That's fair enough. It's not there, it's not there. Does this return null anywhere? This is not great. So data block, the return value. No, it returns some mangled stuff. I would say actually this is stupid. I'll tell you why. It should be like this. It should be, I would say, no, okay, I need to malloc. Well, no, I don't, well. I would say, why malloc every time? Why not do a malloc here? Malloc size of else string. Yeah, you only malloc when you find something. Yeah, you only malloc when, yeah, and you might have null otherwise. Sounds good to me, I would say. I don't know if this is a good, might be a very bad pattern, but it works. So okay, it would be nice to test this. I mean, do an integration test here. Looks good otherwise, but I think, yeah. Yeah, I'm ignoring the int here for now. I don't know if that's relevant. Might not even be, so all that arithmetic I did is irrelevant, but it's okay. One other thing is that, yeah, it's okay. This is not great, but it's fine. Okay, so that would return null in both cases, great. And I think we're good on the search. And are we good on the right? Do we even use this? I don't think we do. Probably don't even need to. Where does this get called? Here. Yeah. I feel like there is a bug somewhere, so we're just gonna. Okay. Let's remove the SSDs. What does bad KV serialize though? I remember that I had a shell script that used bad query. I think 4 queries. Didn't I have that? Anyway, let's make everything. Wait. Okay, for... Okay, let's start at the server. Let's have more keys. Where is this coming from? Max Linux. Something wrong. There might be um can we just see this? Sorry, I have to go. Yeah, can we try? What's max line? Okay, yeah, I kind of guessed this. What did I do here? I think I forgot to... I think we need to go from network order to host order. Great. So we're going to have to go bin server, run this. Okay, here's the problem. Can I get a... I thought I had a debug build. Okay.